Let's talk about finding power series. A power series is a series of the form summation n goes from 0 to infinity of c sub n x to the n. In other words, it's going to be c0 plus c1x plus c2x squared plus c2x cubed, blah, 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 blah. Or more generally, the sum as n goes from 0 to infinity of c sub n x minus a to the n, which is c0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed plus blah, blah, blah. There are different ways to find the power series for a function. We can use the Taylor series formula. We can use the binomial series formula, which we're not going to talk about in this video. We can use addition, subtraction, multiplication, division, differentiation, integration, or substitution with series you already know. These are the series you already know. The series for sine x, cosine x, e to the x, natural log 1 plus x comes in handy. And how about this last one? This is the formula for the sum of an infinite geometric series. For example, let's find the Taylor series for f of x equals sine x centered about pi over 2. The Taylor series for f of x centered about a is the sum as n goes from 0 to infinity of the nth derivative of f at a times x minus a over x minus a to the n over n factorial. In other words, that's going to be f of a plus f prime of a times x minus a over 1 factorial plus f double prime of a times x minus a squared over 2 factorial plus f triple prime of a times x minus a cubed over 3 factorial plus the fourth derivative of f at a times x minus a to the fourth over 4 factorial, etc. See, this is the way we write the fourth derivative. You can't put 4 primes up there. At a certain point, you just bail and you just write that in parentheses. Okay, so when we plug in a equals pi over 2 into this formula, here's what we get. F of pi over 2 plus f prime of pi over 2 times x minus pi over 2 over 1 factorial plus f double prime of pi over 2 times x minus 2 squared over 2 factorial plus etc. Okay, so in order to evaluate these, we need to know f and its derivatives at pi over 2. F is sine x, so f prime is going to be cosine, f double prime is negative sine, f triple prime is a negative cosine, the fourth derivative is sine, the fifth derivative is cosine, and so on. So when we evaluate these at pi over 2, sine of pi over 2 is 1, cosine pi over 2 is 0, negative sine pi over 2 is negative 1, negative cosine pi over 2 is 0, sine pi over 2 again is 1, cosine pi over 2 is 0, etc. And so the values of the function and its derivatives at pi over 2, they just cycle through. 1, 0, negative 1, 0. 1, 0, negative 1, 0. Ad infinitum. Let's plug these into the formula. So again, here's the formula we're plugging these into. We're going to plug these in for f of pi over 2, f prime of pi over 2, the second derivative, the third derivative, the fourth derivative of pi over 2, etc. Okay, so when we do that, we get 1 plus 0, because that first derivative is 0, plus negative 1 times x minus pi over 2 squared over 2 factorial. Again, this third derivative is going to be 0, plus the fourth derivative, that's 1, times x minus pi over 2 to the fourth over 4 factorial. In other words, we get 1 plus negative 1 times x minus x over pi over 2 squared over 2 factorial, plus 1 times x minus pi over 2 to the fourth over 4 factorial. So really, this is it. So these would be the first 4 or first 3 non-zero terms in the power series for that function, the Taylor series. Suppose I ask you to find a power series for f of x equals x cubed times cosine x. Again, let's use a power series we already know. Power series for cosine x, for the Taylor series, Maclaurin series, 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, etc. Just multiply both sides by x cubed, and you get x cubed cosine x is going to be x cubed minus x to the fifth over 2 factorial plus x to the seventh over 4 factorial minus x to the ninth over 6 factorial, etc. How about finding a power series for f of x equals x over 10 plus x squared? The book generally won't tell you about this, but when you want to find a power series for f of x equals some function of the form px to the m all over 1 plus or minus qx to the n, use the formula for a geometric series. a over 1 minus r equals a plus ar squared plus ar cubed plus etc. Now, in Calculus 2, we started with the right side, and then we ended up with this left side as a way to sum the series. But in differential equations, you're going to begin with this side, okay, and then you're going to use it to generate the series. So in this case, f of x equals x over 10 plus x squared. That's not going to cut it because we need this to be a 1 over here. We've got a 10 over here. So let's divide top and bottom by 10. We get x over 10 all over 1 plus x squared over 10. Okay, now we're good to go. So now we can use this formula. You can see that a is going to be x over 10, and r is going to be x squared over 10. Oh, that's great. Or actually, r is negative x squared over 10. Be careful about that because it's 1 minus r, and so if this is 1 plus x squared over 10, that means r is negative x squared over 10. Great. So that means that this function, x over 10 all over 1 plus x squared over 10, is going to be a plus ar squared plus ar cubed. It'll be x over 10 plus x over 10 times r, which is negative x squared over 10, times ar squared. In other words, it's going to be x over 10 times negative x squared over 10 squared plus ar cubed. So it's x over 10 times negative x squared over 10 cubed. Wow, this is getting complicated. But, I'm okay with that as an answer. That's fine. But if you're not okay with it as an answer, here's what you get when you multiply it out. You could write it like this, okay? You've got x, the sum as n goes from 1 to infinity of x over 10 times negative x squared over 10 to the n, which can be simplified, okay? That's negative 1 to the n times x to the 2n, right? Because you can pull the negative 1 out front like that. And then x squared to the n, that's just going to be x to the 2n. And then if you pull this n in here, this x in here, I should say, you get x to the 2n plus 1. So you have negative 1 to the n, x to the 2n plus 1, all over 10 to the n. And then if you plug in n equals 1, n equals 2, blah, 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 you would just end up with this series. Okay, find a power series for f of x equals 1 over 1 minus x squared. Not 1 over 1 minus x squared, but 1 over 1 minus x quantity squared. This is a tricky one. So we're going to write this as 1 over 1 minus x equals 1 plus x squared plus x cubed plus etc. based on the formula for an infinite geometric series. Differentiate both sides with respect to x. 1 over 1 minus x is 1 minus x to the negative 1. So the derivative is going to be negative 1 minus x to the negative 2 times the derivative of the stuff on the inside by chain rule. It's negative 1. The negative 1's cancel, and you're left with 1 minus x to the negative 2. In other words, 1 over 1 minus x squared. So when you take the derivative of both sides, the derivative of this just turns out to be that. And the derivative of 1 plus x squared plus x cubed, etc., is just 1 plus 2x plus 3x squared plus 4x cubed, blah, blah, blah. Suppose the function g of x has power series g of x equals sum as n goes from 1 to infinity of n, a to the n, x to the n plus 2. Find a power series for g prime of x. Okay, here, we're just told the power series in that form. So, let's just take the derivative of that. Okay, g prime of x is going to be the sum as n goes from 1 to infinity of, so you've got the n plus 2. That has to come out front by the power rule. You're pulling that out in front. Times n times a sub n times x to the n plus 1. Because now we've lowered the exponent by 1. It used to be n plus 2. Now it's n plus 1. Find the first three non-zero terms of the power series for f of x, g of x, where f of x equals e to the 5x and g of x equals sine of x squared. Okay, here we're just going to use some substitution. This is a familiar series, the series for e to the x. Let's just replace x with 5x, because we want the power series for e to the 5x. We'd have 1 plus 5x quantity squared over 2 factorial plus 5x quantity cubed over 3 factorial plus 5x quantity to the 4th over 4 factorial, etc. Similarly, we have the power series for sine x. That's burned in your brain, hopefully. And to find the power series for sine of x squared, we just use substitution. We replace the x with x squared. So we get x squared minus x squared cubed over 3 factorial plus x squared the fifth over 5 factorial minus x squared the seventh over 7 factorial plus etc. So when you multiply them together, this is what you end up with. Okay, you multiply this times this. Boy, that looks like a hairy operation. But really, remember that we wanted just the first 3 non-zero terms of the power series. So really, we just want the first 3 non-zero terms of each of these series. Let's multiply them out. So you take the 1 and you multiply it by each of these, and you just get x squared, minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial. Multiply the 5x by this, and you end up with 5x times that same thing. Multiply the 25x squared over 2 factorial times this, pardon me, and you get 25x squared over 2 factorial times that. Okay, and then you pull the x squared. So now we're going to pull the 5x on the inside, multiply all of those by 5x. 25x squared over 2 times all of that. And this is what we end up with. Pardon me. Wow, that looks hairy. So now we just need to order the terms. So first we have an x squared. That's great. And then we have only 1x cubed. And then we have an x to the 4th term. Then we've got some x to the 6th term here. That'll go here. X to the 7th term, that goes here. X to the 8th term goes here. And then we have x to the 10th, 11th, and 12th. Those go at the end. So notice that when you look at the first 3 non-zero terms, this is just what you end up with. So our answer is x squared plus 5x cubed plus 25x to the 4th over 2.